Welcome. Today's lesson is on Le Chatelier's Principle. So let's recall equilibrium. In class, we had a bead activity where you put together beads and then took them apart and eventually reached equilibrium. And you should have learned that the forward reaction rate equals the reverse reaction rate at equilibrium. So the making of the beads and the breaking of the beads were at the same rate. You also should have learned that you don't have to have the same amount of reactants and products to be at equilibrium. You can have different amounts of red beads and yellow beads and beads that are put together. You also should have learned that the total number of reactants and the total number of products is not changing. So when you're at equilibrium, you would have 20 red and yellow bead combos and maybe 60 red separate beads and 60 yellow separate beads. And even though the reaction is still continuing, the net is still the same. The total is still the same. You should have also learned that the actual beads, or in a real chemical reaction, it would be the atoms, that are now reactants or products will change. So even though you had 20 yellow bead combinations and then 20 seconds later you still had 20 yellow bead combinations, they weren't the exact same yellow and red beads that were in the previous combinations. Why? Because some were taken apart and new ones were put together. Today we're going to learn about what happens if you actually upset an equilibrium. So let's say you added more yellow beads or more red beads or more red and yellow bead combos and then started the reaction again. For a chemical reaction, we wouldn't be adding beads. So what if you take a chemical reaction that's equilibrium and you add more of one of the chemicals, or you change the temperature, or you change the pressure if it's gas, or you change the volume if it's a gas, or you precipitate out or somehow get rid of a chemical. What happens to the equilibrium now? Well, that's where Le Chatelier comes in. He said, if a chemical system at equilibrium experiences a change in concentration, temperature, volume, or pressure, then the equilibrium will shift to counteract the imposed change, and a new equilibrium is established. And when we did the yellow bead activity, you did reach equilibrium twice. And that's kind of a long statement by Le Chatelier, so I've kind of made it a little shorter for you. And here is my version. If you change a system at equilibrium, the system will try to undo the change. So let's take a look at an actual chemical reaction, and we did this demo in class, so this should be familiar to you. Here is the reaction that we did in class. We had cobalt, which is called a complex ion because 6 waters are attached to it, reacting with 4 chloride ions and 50 kilojoules of energy. So this is an endothermic reaction to produce cobalt tetrachloride, 2 ion, minus 2 ion, and 6 water molecules. And the water is important here because the reaction is done in alcohol. So we actually do have, which is unusual, a concentration of water molecules. So here is the reaction. And what is interesting about the reaction is also that this molecule here has a pink color and this molecule here has a a blue color. And they will reach equilibrium. So the bottle that we had sitting at the front of the room was already at equilibrium. But what happens if we do something to the system to upset the equilibrium? Then what happens? Well, let's say I do these following changes: add water, add heat, or take out some chloride. So what happens if I add water? Well, according to Le Chatelier, if I add water, the system will try to do the opposite or undo the change. So if I add water, the system will try to get rid of the water. So I have a reaction that goes forward to the right and reverse to the left. And if I need to get rid of water, I added water here, but to equalize again, I'm going to get rid of that water. The reaction in reverse speeds up, to get rid of that water. So we call that, since the reverse reaction, this direction speeds up, we call that shifting to the left. So if it shifts to the left, then everything on the left side will go up in concentration, and everything to the right side will start to go down in concentration. So the cobalt with the water goes up, the chloride goes up, the cobalt with the chloride goes down, and the water also goes down. But you may also notice that we started with the water going up, and now some of it goes down. So what is it? Is it exactly the same as it was before? No. Actually, the net is still slightly up because we didn't get rid of all the water we added. We got rid of some of the water we added. So if I shift it to the left, on the left side there is a pink molecule, then the color should be pinker than when we started. So if I take this reaction, if it started off more blue and I add water, it should go pink. And that's what happened in class. So hopefully you remember that. So let's take a look at a few more, and hopefully you get the hang of this. What happens if I take the equilibrium and now heat it up instead? So Le Chatelier says if I add heat, the system will try to get rid of the heat to undo the change to get it back to equilibrium. So how do I get rid of heat? Well, let's take a look at this reaction. Here's basically the heat in the reaction where the kilojoules is. If I go to the right, that direction is an endothermic reaction. The reverse reaction going to the left is an exothermic reaction. So to get rid of heat, to get rid of this, I need to go shift towards the right. And that's what happens. I will shift towards the right. Then everything on the right side of this reaction will go up, and everything to the left side will go down until I reach equilibrium again. So that's what we have here. Everything to the left goes down and everything to the right goes up. Well, if the right side is a blue molecule, then the color is going to become bluer than it was before. So there we have the reaction. If you add heat to it, it becomes blue. All right, so hopefully you're watching this pattern. Let's do the next one. What if I take out some chloride? And you go, Miss Backus, how can I reach into that beaker and take out the chloride? Well, that would be very hard to do. But you can do it chemically. So how do I get rid of the chlorided solution? Well, one of the things you could do is precipitate it out. So I can add something that precipitates with chloride. In class, we used a lead nitrate to precipitate it out. So if I precipitate it out, I will be getting rid of the chloride. If I get rid of the chloride, so there I'm getting rid of my chloride, which direction does it shift? So push pause on the video and see if you can figure it out before I give you the answer. So if I take out the chloride, the system will try to make more chloride. So is it going to go towards the right or to the left? So pause the video and see if you can get the right answer. Welcome back. I hope you really did pause it. And let's see, did you say left? So if I get rid of chloride, the system will try to make chloride. How do I make chloride? By reversing this reaction. So everything on the left will go up and everything on the right will go down. So that's what we have here. Now notice once again I have two arrows here. I took some out so it went down, and then I made some more, it went up. So what is it? Is it equal now? Is it more or less? Well, the original case I took some out. The system never gets rid of all of it. It only gets rid of some of it. So yes, the net is actually still down. And what color does it become? Well, if I go to the left and the left side has the pink molecule, then it's going to become pinker. And there you have the last situation. If I take out some chloride, there's less chloride, the solution becomes pinker. So there you have an example of Le Chatelier's principle. Hope you take good notes and see you in class.